Our next graph algorithms topic is kind of a big one, and so I suppose this might be a good time for a breather lecture, although personally I don't see why anybody would ever need a breather from graph algorithms. But there is this data structure that we're going to have to discuss before we can get to our next topic, and as it turns out, there are actually applications of this data structure in graph connectivity. So it seems like it's the perfect time in the sequence to talk about this. Before we talk about this, though, I want to show a photograph. Here it is. This is a photograph taken from 6 billion kilometers away, and it depicts the planet Earth. See if you can find it. It actually is visible if you know where to look. It's right here. This photograph is often called the pale blue dot photograph. And I'm pleased to say that I'm in this photograph, and you're in this photograph too. If you were alive on February 14th, 1990, when this photograph was taken by the Voyager 1 spacecraft from, as I said, 6 billion kilometers away. The light from planet Earth traveled for about 5.5 hours to reach the camera when this photograph was taken. Now, just hold this in the back of your mind. I'm going to come back to this later in this lecture because I want to talk about our sense of scale, our ability to perceive very large distances or very large objects or very large numbers. It's just something to mull over. In the meantime, let's go back and talk more about graph connectivity. So consider again the problem of, given some undirected graph G, identifying all of the connected components of G. Now, we've been through this, we know how to do this. We also know, of course, that connectivity problems always are very easy for us as humans when we have a nice, convenient diagram. We know that what we want here is the ability to take each component, wrap it all up, and then let's say call this one component number 1. And then this might be component number 2. And one way I could do this, identifying the components, is to just tag each vertex with its component number. I could do this by means of this table here or any other mapping that I see fit. So any way of mapping each vertex to some identifier of its component. We already know that we can do this with a sequence of graph traversals, a sequence of disjoint graph traversals. And the trick here is that although we might have to start multiple traversals, we only ever visit each vertex once, which means if we work out the running time of the whole process, it ends up being linear in the number of vertices and edges. And we also understand that for global properties of graphs, and certainly the connectivity of the graph or the set of components is a pretty global property, being able to do things in linear time in the number of vertices and edges is pretty much the gold standard. It would be very difficult to assess connectivity without looking at every vertex and every edge at least once. Okay, so I run this sequence of traversals, and then I can just label components, let's say using a number, although really I just care about having some way of identifying which vertex is in which component. I don't necessarily have to use numbers to achieve this, although this table of numbers certainly gives me an easy way of doing that. Now suppose I've already done that, and you ask me the question, are vertices C and D in the same component? What we can observe is if I already have this mapping, which here I've drawn as a table, it's really easy, assuming that it's easy for me to look up a particular vertex in the table, it's really easy to answer this question. So the answer here is no, because if I look in the table, vertex C is listed as being in component number 2, and vertex D is listed as being in component number 1. And the answer is dead easy because all I have to do is compare those values together. I just look in the table and check whether I have the same identifier under vertex C as I do under vertex D. So once I've identified the components, it's really easy to test whether two vertices are in the same component because the component number can be looked up, in constant time. Now, I'm not going to go too far into this, but I want to observe, as I usually do, that I've chosen to represent this component mapping as a table, and I could do that. That is, I could write code where the components are stored as some array that maps a vertex to a component identifier. I could also choose to do it by storing the component identifier as sort of a field on my vertex object. So instead of using a separate table, if I'm using objects to represent vertices, I could always add a field to it saying, what's the component number of this vertex? And that means if I have two vertices, looking up the component identifier is constant time. Also, if I choose to use an actual table and I choose to number my vertices in advance, and we talked about when we discussed graph representations why that is generally a good idea if you're using tables, if you're storing your adjacency list or adjacency matrix using plain old arrays or lists, then I might have something, a table that looks more like this. There's V0, there's V1, there's V2, and you can see how, because each vertex has a number, if I want to access the element of the table for a specific vertex, I'm just doing straightforward array indexing. So in any event, there are plenty of paths towards being able to perform these lookup operations in constant time. Okay, well, here's the slide saying the thing that I just said. There are lots of different ways of storing this data, but there are definitely ways of doing it that allow us to use constant time lookups. So whether I use a table, whether I just tag each vertex using some field, it doesn't make much of a difference because there definitely are ways to achieve this in constant time. So what about this though? Suppose that I've computed my table of component identifiers, component numbers, and then I modify the graph. And I don't usually bring this possibility up. Like, think about this. We've talked about a lot of graph algorithms, and we generally treat them as a one-off thing. I have a graph, I run a traversal, and then that's it. And maybe I modify the graph later and run more traversals, but we haven't really discussed what happens if I store the result of some graph algorithm and then modify the graph later. So suppose I've already computed the components of the graph, so I know the components of the graph as of this point, as of the graph being in this state here, and then I add this edge. So pretty clearly, adding this edge changes the structure of components of the graph. So this information will probably become out of date. Now, one other observation I'm going to make that we don't need too much for the coming slides, but it's worth pointing out, is that this particular model, whereby I ask questions about whether two vertices are in the same component using pre-computed component information, it makes sense that if I were doing this, the only reason I would want to do it this way versus doing it from scratch is either because I've pre-computed the components for some other reason, or because I intend to ask lots of questions of that type. So if I know in advance, I'm going to make lots of queries along the lines of, here are two vertices, are they in the same component? Well, then it does make sense for me to pre-compute the component of every vertex so that each of the queries is a really easy constant time operation. On the other hand, of course, if I just have a graph and I want to know whether two vertices are in the same component and be done with it, I only have one query to make, then it doesn't make very much sense to find all the components. That is, if all I have is this one graph and only one question to answer, are vertices C and D in the same component, well then I could just run a traversal starting at vertex D and then see whether I end up reaching vertex C. And if the answer is no, well then they're not in the same component. So the reason why I'm pre-computing here might be because I'm working with an application where I have to ask lots of questions of that form, or an application where for some reason I need to find the components for some other purpose, and then I can just recycle that data. So the question is, in a context where I want that benefit, where I want to use this table of component information, what do I do in the situation where I add an edge? So the idea being, if I'm going to ask lots and lots of questions about the components containing particular vertices, then logically I'm going to need to store this table over a relatively long period of time. And it makes sense, if graphs can change, that the graph might eventually change, and I have to figure out how to make my table catch up with the new information. So a few observations I can make. Well, logically, if I add an edge to the graph, that could affect what I know about the components of the graph. That is, a table of components could get stale. It could be suddenly out of date. It isn't guaranteed to be out of date, but certainly in this case, the structure of components of the graph is changing. If I wanted to, I could just, whenever a new edge or vertex or whatever is added to my graph, I could just fully recompute the set of components. So I could run another set of traversals and then recompute this entire table every single time one edge is added. But the problem is, it feels to me as if that's rather inefficient. It feels like I'm doing a lot of work I don't need to do. So I notice that when I add one edge, okay, an edge has two endpoints. So either the edge that I add is going to link two vertices in the same component. So we'll go back over to the state before I added the edge. Consider all the ways I could add one edge to this graph. Okay, I could add the edge between K and H. Notice that that changes nothing about the components of each vertex because I'm connecting a component back to itself. I am adding a new edge, but it doesn't change how many components exist. I could also add an edge between L and R. That also changes nothing about the components because I'm just adding an edge within a particular component. On the other hand, if I add an edge from N to K, well, that's going to affect two different components, the two endpoints of the edge, but that's it. An edge only has two endpoints. It's not going to affect this component at all. None of the vertices touched by my new edge are in this component or the component over on the left. If I add the edge EL, we can see that the effect of adding that edge is effectively to merge these two components together. But these other components that I already had are completely unchanged, and it's not difficult to guarantee that that will be the case, because the new edge that I add will affect at most two components, that is, the two endpoints of the edge, if those are indeed in separate components. So my observation, basically, summing all of that up, is when I add some new edge UV to the graph, either U and V are in the same component, and so nothing happens. Basically, we just add a new edge and the components stay the same, or they're in different components, and the effect is to merge those two components together after the edge is added. Now in this graph, there are 4 components. Currently, I'm about to add an edge that makes there only 3 components. There could be graphs out there with thousands or hundreds of thousands of components. And I mean, obviously you probably have considered that possibility. I'm actually going to do an experiment at the end of this lecture that refers to graphs with thousands of components. If we know that adding one edge will only affect at most 2 different components, then certainly if our graph has thousands of components, we really want to avoid fully recomputing the set of components. We can see there's going to be a lot of wasted effort that goes into that recomputation because a lot of components will definitely not have changed. So what I'm wondering is there a faster way of updating the component information so that the table is still current without wasting lots of time repeating work that I've done before? So what I could observe is, of course, this new edge is only going to affect vertices in the 2 components that it links. Effectively, what I'm doing is just merging them into one big component. I have a few ways of doing this. One option I can think of is, I guess I have to at least, at minimum, I have to change the entries of the table associated with the affected vertices, or I have the potential of needing to change them. One option I have to avoid changing too much of the table is just to keep all the vertices in one component and bring all the vertices in the other component into the first component. In this case, I observe if I decide that, so this thing over here is component number 1. If I decide to put C, L, and R into component 1 by modifying the table, I have to iterate over everything in the second component. So I just erase component 2 from existence and put all the vertices into component 1. The reason I think that's a better idea than the alternative, which is putting everything over here into component 2, is that I have to iterate over everything in the component to achieve this. And this component is smaller, so I'm changing fewer things in the table. So it makes some sense to move everything from the smaller component to be part of the larger one. So if I track components through some kind of numbering scheme, and I want to merge components Ci and Cj, what I could do is just go through every component, every vertex in component Cj and set its component number to be I. And as I said, I guess intuitively it makes some sense that I'd want to choose the component I merge in to be the smaller one, so I change fewer entries of the table. Although interestingly, based on the data I have on this slide, the only way of knowing what's in component number 2 is iterating over the entire table anyway. So it looks like if I want to reset the component number of everything in component 2 to be component 1, that I'm going to be spending linear work. I'm going to be iterating through all the vertices to find everything in component 2. But no matter how I'm storing my components, I run the risk of having to spend linear work changing the table to put everything in one of the components into the other of the 2 components. So the issue with this type of adjustment is that modifying the component number of every vertex in one of the affected components could be linear time no matter how I do it, if I'm modifying every entry of the table for those vertices. And the reason is simply because I could have a component that contains, well, okay, if I always modify the component number of the smaller component, we can assume that if there are 2 components that I'm merging, the smaller one will have size that less than n over 2, because it makes no sense to have 2 components, both of whose size is greater than n over 2. That doesn't make any sense. On the other hand, if my component has size, I don't know, n over 10 or n over 100, well then modifying the component number of each of those vertices, n over 100 vertices, well that's going to be big theta of n over 100, which we know already is the same as big theta of n. And so that's going to be linear time. And so the issue here is if I have to go through and modify a table entry for every single vertex in one of my components, there are lots of cases I can think of where that could require linear work in the number of vertices. This is still an improvement over running a new set of traversals. That is to say, I am only modifying table entries for the vertices that are actually being affected by this merge, although there could be a linear number of them, and the running time is no longer dependent on the number of edges, just on the number of vertices. So both of those are improvements over running a full set of new traversals that require big theta of v plus e time. But naturally, of course, I have the usual question here, which is, can we do better? So yes, I can merge 2 components by adjust the table to account for adding a new edge, I could merge those two components in linear time. Is there a way I could do it faster than that? Because it feels to me as if adding an edge is a very local operation. Sure, it does affect vertices far away from where the edge is added, but if I find some way of structuring my data, maybe I can make the merging of components a relatively local operation as well. And to do this, basically we have to define a data structure. It turns out this is a data structure problem, and maybe that was obvious and maybe it wasn't. So to me, I've mentioned before that I sort of view data structure problems as the things that arise when you think of an algorithm that needs to be frozen in time. That is, I could use an algorithm to compute my components, but what if I want to compute components and then sit on that data for a little while, put it in this table, do nothing with it for a while, and then come back later and modify it because the component structure changes? Well, what we've done with graphs so far has been primarily algorithm-oriented, that is, perform one task continuously until it's done. We now have a data structure problem because I want the ability to perform my algorithm in pieces. I want to find some components, modify the graph, find some more components, and maybe in the meantime ask questions about which vertex is in which component. So it seems like I'm working with a data structure problem. It also seems, frankly, like this data structure that I need isn't graph-specific. Really what I want to ask is, if I have this table that maps elements, whether they be vertices or something else, to sets, so we've got everything in set 1, we've got everything in set 3, we've got everything in set 4, is there some fast way of merging sets together that allows me still to ask which set contains a particular element? That doesn't really need to be restricted to a graph to be a valid data structure. It's mostly a question about sets. Before I talk about the data structure, though, I want to observe something about the merging procedure, which is, if my ultimate goal is just to ask whether two vertices are in the same component, I don't really care whether my components are numbered. All I care about is there is some way of distinguishing which component a vertex is in. I also want to observe that my numbering scheme begins to fall apart if I do merges. So notice how originally, before the merge, I had 4 components. I had component 1, that's everything over here. I had component 2, that's everything here. And then I also have components 3 and 4. Once I'm done merging, I add everything in component 2 into component 1, but I change nothing else. And so you'll see after the merge is over, I have component 1, I have component 3, and I have component 4. There is no component 2. That's not really a big deal, but it makes it pretty clear that I don't care that much about the component numbering. The numbers are just something I use to determine whether vertices are in the same component as each other. It makes no difference to me what number I assign to a particular component for this application. And so before I talk about the data structure, I want to observe that there are lots of things we could put in the table that we can use as a way of identifying a component. We don't have to use a number. In fact, what I could do is observe that in this technique, where I use a series of traversals, when I go through my graph to perform traversals, I would have probably identified my original component number 1 by doing a traversal rooted at vertex A. When I identified component number 3, I probably began my traversal at vertex F. So what we could do is decide that instead of numbering our components, we could just elect one vertex of each component to be the designated spokesperson for that component, the designated representative. And if we want to distinguish between components, we could just list each vertex along with its component's representative. So A has been elected the leader of component 1. And that means if I look up any vertex in component 1 in the table, the table just tells me this vertex is a member of the same component as vertex A. If I go look up, let's say, vertex N, I can see that the table tells me this vertex is a member of the same component as vertex F. So in a sense, we choose a representative vertex of each component and use that as the identifier for the component. If I do a bunch of merges, I get the same effect as before, but the numbering scheme, which uses these external identifiers, numbers that don't appear anywhere else, isn't really necessary for this. All I need is some way of unambiguously distinguishing which component a vertex is in. I can do that with numbers, I can do it with some other identifier, or I could just choose one of my elements, one of my vertices, to represent each component, to be the designated representative of that component. And so in the case where you isolate your components via a sequence of traversals, I guess it seems natural to me that you would just set the representative for each component to be the vertex at which you started the traversal of that component. So in this case, vertices A, F, C, and G become the representatives of their component. But you could choose that representative however you wanted. The key thing is everything in the same component maps to the same representative. That's how you know that they're in the same component. And what's nice about this is that we don't have to wring our hands too much about the numbering being broken. Not that it makes a difference, but it feels sort of wrong to have a numbering that we then poke holes in by performing merge operations. Okay, so I think we're ready to see the data structure that we need to work with here. We don't really care that much about vertices. Vertices are vertices and components are one application of a data structure that we need. But really, the operations I've just been discussing, the ability to look up which component something is in, and the ability to merge components can be phrased much more naturally just in terms of sets, just in terms of, I guess, a disjoint set of sets, because each vertex is in only one component at a time, and every vertex must be in one component. So I have this collection of elements, in this case the vertices of a graph, a universe of elements, and I want to partition them among a bunch of different sets. I want to retain the option to efficiently answer the question which set is a particular element in, and I want the ability to merge two components, two sets together efficiently. That leads me to a data structure called a disjoint set data structure. I've chosen to give it the proper name of the Disjoint Sets, ADT, because I wanted to make it clear that this data structure represents a bunch of different sets, not just one set. Although in conversation I call this thing a disjoint set data structure, so I don't pluralize it. Okay, so formally, a disjoint set data structure represents a collection of disjoint sets. Let's say that there are k of them, although we'll see very quickly that we don't care that much about the names of the sets or how many of them there are, because that keeps changing. So let's say there are k disjoint sets over some universe of elements called U. And we enforce the following two constraints. Any two sets, although this assumes that I is not equal to j, any two distinct sets always have an empty intersection. That is, there is no element that is in two of these sets at a time. Each element is in at most one set. And if I take the union of all of my sets, that equals my universe. In other words, every single element in my universe is in at least one of these sets. No element is in two of these sets or more of them, which means, of course, we can infer from that every element is in exactly one of my various sets. So for the sake of talking about merging components, I would probably set each of my sets to contain the vertices in one component, and that means the universe U would be the entire vertex set V of the graph that I started with. But nothing about this data structure requires us to be working with graphs. Another thing I'm going to observe about this data structure is that it has the bare minimum number of operations, although actually there are some sources that don't even have this. They only have these two things, find and union. And the reason why I have added the add operation is it does give us some way of adding new things to our universe. It's a pretty intuitive thing to do. There are some sources that don't allow an add operation. They instead assume that when you create the structure, the universe is predefined. That is, you have to decide on the universe before you even start working with your sets at all. Okay, so the operations of my disjoint set data structure are, I can add a new element to my universe, in which case we begin by adding it to a set all by itself. For any element in my universe, I can call the find operation, which returns the designated representative of the set containing that element. So at any given time, each of the sets in my collection has a designated representative element. And the find operation gives me the representative for every element set. And that's one way of deciding whether two elements are in the same set or not. And then there's the union operation that takes two elements and merges the sets containing them. If both elements are in the same set, then the merge does nothing. We're just merging a set with itself. Otherwise, we irrevocably turn those two sets into one bigger set. You will see here that although I have the facility to take the union of two sets, to join the two sets together, there is no operation to split them apart again. This data structure has the bare minimum for the application that we were just discussing, the connected component application. We already know that the more operations a data structure has, the harder it is to juggle the different operations. So this is a very Spartan data structure. It has very few operations. Some operations are irreversible, but in exchange, maybe we can design an implementation that's really efficient. If we know that we can never undo a union operation, maybe that means that our problem is easier to solve, and it's easier to get a really fast algorithm for union. What we're going to see of all the data structures that we've worked with in this course, and probably all the ones we are going to see, data structures that can contain an arbitrary number of elements, this may well be the one where every operation has the fastest running time we see in this entire course. By having such a restricted data structure, we are able to produce unbelievably good running times on these operations. Okay, so every element of my universe must appear in exactly one set. I can add new elements to my universe with the add operation, but I can't remove them. Once they're there forever. I can also merge two sets together with my union operation, but I can't undo that either. Once they are merged forever. Now, the number of sets in my collection changes every time I merge two of them together. And because the union operation could be called on two elements that are in the same set, it isn't even that clear necessarily whether a union operation will change the number of sets. But either the number of sets stays the same or it decreases, because every union that merges two distinct sets will reduce the total number of sets once it's finished. And so sets themselves, notice how nothing in this abstract data type provides you access to the elements of a set directly. All you're allowed to do is ask questions about whether a particular element is in a particular set, and you do that by looking at its designated representative. In general, the only way you can refer to a set is by its representative, not by any other name the set might have internally. Now, to be clear, I'm referring to a property visible from the outside. So when you use a disjoint set structure, you have no way of knowing how many sets are in the collection, except, of course, by looking at everything in the universe and asking questions about what set those things are in. If you're implementing the data structure internally, well, of course, you can store the sets however you want. You could store them as a bunch of separate things, in which case internally you would have access to that information. But the people using the data structure are not entitled to know necessarily how many sets there are unless they figure it out themselves with repeated calls to find. Now, I've just said a bunch of things. I want to do a few examples because although find and union are described here, it isn't necessarily obvious why I've defined them this way. So here's an example. Consider these three sets. And notice that they are disjoint, and suppose that I have chosen, I as the person implementing my disjoint set structure, have chosen the representatives to be E, B, and G. Now, what it means for something to be chosen as a representative is sort of up to me. I know that every set must have one designated representative element. It's really up to me as the implementer to decide exactly how I choose that representative. We're going to see pretty quickly, though, that there are some obvious choices that we can make. Now, as I mentioned, the sets themselves have no real identity beyond the elements in them. And because I can uniquely identify a set by referring to any of its elements, in fact. So if I say, let's talk about the set containing element D. Well, only one set contains element D, so I could figure out which set that was only from that information. However, of course, we can uniquely identify a set by referring to its representative. And in general, that's sort of the convention we're going to follow. If I want to talk about the first set, I will talk about the set represented by E. If I want to talk about the last set, I will talk about the set represented by G. Now, the find operation, which we saw a few slides ago, takes any element and then returns the representative of that set. So if I call find on A and I call find on H, I will get E in both cases because E is the representative of that set. In fact, if I call find on E, I will also get E. Notice that this means I can use the output of the find operation to decide whether two vertices are in the same set or not, because if find returns the same representative for both of those elements, then that means they must be in the same set. Whereas if I were to call find on C, I get B, which is the representative of that set. And if I call find on F, I get G. So two elements U and V are in the same set if and only if the return value of find is the same for both of those elements. Now, I'll point out in a minute that the find function is something that we should call only when we need it. That is, if I call the find function, I shouldn't save the result for later, because the result of the find function may not persist over time. I'll come back to that after we've talked about the union operation. So the union operation merges the sets containing two given elements. So I can call union with any elements I want. I don't have to use representatives. So I could say things like, compute the union of, merge together the sets containing A and the set containing I. Or I could say, merge together the set containing E and the set containing B. Or I could say, merge together the set containing D and the set containing H. Now think about that last one. If I say merge together the set containing D and the set containing H, well, D and H are already in the same set, which means the merge operation does nothing. In a sense, it's already done. They're both already in the same set. So I'm going to call this a trivial union operation, and they're allowed, and I'll come back to it a few times, but for the most part in this lecture, when we talk about union operations, we're talking about ones that actually perform some work. That is, we actually take two sets and turn them into one. So as I mentioned earlier, there is no facility to undo a union operation. Once I have merged two sets, they are merged forever. That's it. Until I create a new disjoint set structure, those two sets are merged forever. All right, let's try doing a merge. Merge the set containing A and the set containing G. As we'll see shortly when we talk about implementations, typically the first step of a merge operation is to find the representative of each set, just so you know which set you're working with, although we don't have to do it that way. So notice how I am merging the first set and the third set. That's the merge I want to do. Okay, so a merge, no matter how I implement it, has to have the effect of turning these two things into one big set. So I guess I could just add f, g, and I to this big set here. Okay, and then once I have that, I have to make sure, so I only have two sets in my system now, I have to make sure that the sets I end up with all have a designated representative. I'm allowed to choose a different representative if I want, although you can see that based on the way I did this, it makes sense just to keep E as the representative here. Like, why would I bother changing it? But I am allowed to change it if I want to, and the next slide points that out. So suppose in an attempt to be contrary, I merge them together, and then as the representative of the combined set, I choose element D. That's allowed. I'm allowed to do that. Although in practice, just because it's convenient, that is, there's no point in choosing an arbitrary element when you could just choose one of the existing representatives of your two input sets. There is no requirement that you do that, but yes, in practice, the new representative of the combined set tends to be one of the representatives of the sets that you started with. So suppose I choose D as the new representative, which I am allowed to do even though it's sort of a weird choice. Notice that means the representative associated with each element does change over time. So whether I chose E or D, there are some elements, the ones that were in the old set at the bottom, so F, G, and I, those previously had G as their representative, and now, once I'm done, they're going to have D as their representative. And so it's still true, though, that if I call the find operation, so if I call find on F, then I get D. If I call find on I, then I get D. And that means if I want to test whether F and I are in the same set, well, I could just call the find operation and see whether it returns the same result. That is still true no matter what. Remember, though, that the return value of the find operation could change over time, because sets get merged, which means if you want to use the find operation to test whether two elements are in the same set, make brand new fresh calls to the find operation every time you want to do that test. Don't save the result for later because the result might be out of date by the time you need it. Okay, well, let's turn now to the question of implementation. So, as usual, fundamentally we are representing a collection of things. So it's a collection of stuff broken up into disjoint sets. And you know already that my technique typically is, if I'm representing a collection of things, let's just start by using arrays or lists. And although we know that linked lists have asymptotically better performance for a lot of operations, it is true that people, and I'm one of them, seem to like using arrays as the basis for a lot of things. Even though linked lists could be theoretically superior, they have a lot more overhead. And we've even seen that in terms of talking about stuff like dictionaries and priority queues. I want to compare any complicated, let's say, binary search tree or a heap representation that I come up with against how would a regular array perform, because that's one way of knowing that my complicated representation is worth it. So I'm going to do the same thing here. However, here, for some reason, I'm going to start by saying, let's use doubly linked lists. I'll explain why that's my instinct in a little while. There's a reason why I don't default to arrays here, and why I think arrays wouldn't be a good choice for this application. It has to do with the fact that linked lists have a bit more agility as far as the merge operation goes, and I'll come back to that in a little while. So suppose I want to represent a collection of disjoint sets. What I could do internally inside my data structure is store each set as a linked list. I'll use a doubly linked list, and I'll explain why it has to be doubly linked in a minute, and then shortly thereafter go back on that and try using singly linked lists instead. So I've got three different sets, there they are, and I represent each one with just a list of elements. Okay, so then I have to choose a designated representative for each set, and I want some, methodical choice. So to me, what seems obvious is I'll just choose the first element of each list to serve as the representative of that set. And what's nice about that is if I run the find operation and I ask you, give me the representative for D. Okay, so you have the node with D in it, and then you just walk forwards in my doubly linked list until you get to the front, and then you say, okay, the representative is E. If I ask you for the representative of M, you just walk forwards until you're at the front, and the representative is B. If I ask you for the representative of B, you try and walk forwards, you realize you're already at the front, and so the answer is B. So I just choose the first, I adopt the convention that the first element of my list is always my representative. Okay, so now the question is, how do I do a merge? So suppose I want to call the union operation to union M with, let's say, J. So I want to merge these two sets together. And here's where linked lists give me a great benefit. So I want these two sets to be one big set, and I've chosen to represent my sets as linear sequences, that is to say lists. So what I want is to turn these two lists into one long list. What I could do is just attach one list to the end of the next one. And now I've just got one long list. I just make this into one big list, and then I clear this out as being its own set. It's now just part of the set above it. I end up with something like this. So to merge two sets, all I do is join the list for one set to the end of the list for the other. And so I end up with a, again, doubly linked list that contains all of the elements of the set. If I now call, let's say, the find operation on L, well, then I have to walk all the way from L to the beginning, and the representative is E. If I call the find operation on A, the representative is also E, which means, of course, that L and A are in the same set, which is exactly what I intended as a result of this merge. Now, this is the reason I chose doubly linked lists for this, is that attaching one list to the end of another is constant time. Once I have a pointer to the two things I'm attaching together, I just have to modify some pointers. If I wanted to merge two arrays together, that could be nasty because as usual, assuming that the array could be full, if I want to merge this set of size 6 with this set of size 4, and they're stored in arrays, I would have to make a new array of size 10 and copy everything in, versus with doubly linked lists, where I could just attach the two lists together in constant time, once I have a pointer to the beginning and end of the respective lists. So okay, the find operation is pretty clearly linear because I could be in a situation where one of my sets has size that is linear. Now it doesn't have to actually be n, it could be, n over 2 or n over 10 or something. But if I start at the end of a list and have to walk all the way to the beginning, well, that's going to take linear time in the size of the list. The list could have linear size in terms of n, and that means I'm looking at an operation that's linear time. The union operation, although the most characteristic part of the union operation, that is adding this extra link, that's actually constant time. Once I have a pointer to the B and a pointer to the K, adding the link between them is constant. The problem is, remember that a union operation can be called on any two elements. So if I say union L with A, what I have to do is find the end of the list containing A, and the beginning of the list containing L. I'll go back to the original state. So I have to find the representative for L, the beginning of that list, and the end of the list containing A. The problem is that could require iterating in both cases through a linear number of things. So although adding the link itself is constant, finding the two nodes to join together could take linear time. So what I've ended up with my basic doubly linked list solution is an implementation where both find and union are linear. And to be honest, that isn't really that impressive. That is, there are a lot of basic implementations I could think of, arrays and lists, where I could come up with basically linear time. That's fine, but it isn't the amazing performance I was hoping for. On the other hand, I'm being a bit too hard on myself here. I'm enforcing a lot of rules on my linked lists that I don't need. So for example, what exactly am I using when it comes to these linked lists? Like I've chosen linked lists because they allow joining things to be very quick. But when I think of other list operations that I need, why do I need a list specifically? A list in this case being a linear sequence in order. I don't know that I need that. I just need the ability to take every element and walk from there to their representative. So I have to start at some element and walk to the beginning of the corresponding collection. And then that's the representative. I also need the ability to perform merges. I don't know that I need a doubly linked list for that. So let's think about what happens if I switch to a singly linked list. Now, I know full well that going from doubly to singly linked lists doesn't give me an asymptotic benefit, because a doubly linked list is just two singly linked lists overlaid back to back, effectively, like it's just pointers in two directions. But maybe if I can prune down some of the things I need, I can find a representation that's more efficient. So I notice that the find operation only ever travels through the list in one direction. That is, if I call find on D, I just walk towards the front. I don't need to walk in the other direction for the find operation. So I ask myself, do I really need a doubly linked list? And the answer is, well, maybe, because it depends on how rigidly I enforce the mechanics of that merge I defined earlier. So for the merge operation, if I want to do the merge exactly as I defined it earlier, where I join the beginning of one set to the end of the previous one, well, in that case, if I say merge H with M, I have to find the beginning of this list and the end of this one. And that's going to be a problem if I only have a singly linked list. So without a doubly linked list, how would I make this join? If I say merge H with M, then how do I go from H to K? I can't. The pointers don't point in that direction. So it's not possible to find the end of a list if all the pointers point towards the beginning. So my question is that non-negotiable? Like, do I really have to do the merge this way? The reason I want to do the merge this way, by joining the beginning of one list to the end of another, is that when I'm done, I have my linear sequence. I have a single linked list. But I was just saying I don't need a linked list that badly. I just need certain linked list-ish behavior. So I wonder, do I have to perform the merge this way? Or couldn't I maybe do a merge like this? Why not just join the beginning of one set to the beginning of another set? Let's think about this. What do I need to do when I'm done? Well, I need the ability to ask the question, given some element, what set is this in? I need to find the representative. If I follow pointers from L, sure enough, I end up at E. I end up at the correct representative. I don't need to pass through all this stuff. And actually, that's when I realized this is actually a better way of doing it, because I was able to go from L directly to E via the stuff that was in the same set as L already. I didn't have to follow this circuitous path all the way through the elements of the other set. So if I implement my merges this way, and it's worth adding, this is no longer a linked list-based structure. This isn't allowed, this example of this representative that has two different things attached to it. That's not a linked list. A list is a linear sequence. But if I implement it this way, whatever this thing turns out to be, if I implement it this way, not only does everything still work, I no longer need double linkage, I don't need a doubly linked list, and I can see a case where, although maybe it's a constant time speed up, it seems as if doing a merge this way is actually to my benefit. I actually save a few operations as a result. So the whole point of this one-way list structure is to make the representative available from anywhere in the list. There's no requirement that I maintain the set as an actual list. I just need some path. The word path reminds me of certain other data structures. I just need some path from every element to the representative. I don't care necessarily how many elements connect to the representative. In general, in fact, I don't even care that much if after a bunch of merges, I have a situation forming sort of like this. I have a whole bunch of different things that are all attached to one node. Because as long as I can go from every element to the representative, and as long as I can perform merges by tying one representative to the representative of a different set, well then I can do both union and find. I don't require a linear sequence. I don't require a list. I don't mind if I follow a pointer out of each thing, as long as I can get back up to my representative. Okay, wait, up. Isn't this a left to right diagram? Yeah, it seems like my brain is hinting to me that what I'm working with here isn't a list at all. It's a tree. This is basically just a tree that I visualized sort of sideways. Okay, so let's fix that. I basically have something like this. The resulting data structure, when I really think about it, if I turn my head on its side, is basically a form of tree. It's the kind of arbitrary tree, it's very clearly not a binary tree, it's the kind of arbitrary tree that I could easily represent with a parent array, because each node contains just a pointer to its parent. That's it. Now, whether I choose to represent this as a parent array in a table, or whether I choose to represent it as a bunch of node objects, each with a pointer to their parent, it makes no difference. Effectively, this is exactly the same kind of tree I might represent using a parent array. Okay, so I'll adopt the convention that what I now have to represent each of my sets is a little tree, and the root of that tree is its representative. If I want to know the representative for a particular element, like k, I just walk up from that element to the root, and then the representative will be D. Now this is great. One, because we're now working with trees. For a minute there, I thought we were going to have to go through this lecture talking about sequence types, but fortunately, we ended up talking about trees. And two, because it's already sort of clear that the operations we need to perform are going to be based on upwards traversals in trees, upwards paths. And we know we have a sort of long tradition in algorithms. If we think back to binary search trees and heaps and things, we have a long tradition of being able to find pretty efficient algorithms, pretty efficient representations when we can reduce our operations to finding upwards paths in trees. Typically, that involves proving that the height of the tree is bounded by some relatively small value. Now, a note about a few things here. Notice how the nodes in this tree structure do not store pointers to their children. That can be sort of liberating because it means that we don't have to worry about things like what's the maximum number of children a node can have. Now, to be clear, it doesn't matter how many children nodes have. There is a way of representing the tree such that you can walk downwards in the tree. You could keep a list of child pointers, but we don't need that here. All I need is the ability to get from any element to a representative. I don't need to go back down. Because I am representing it this way, I have a very simple representation, which is going to be helpful for me later, but keep in mind, I can't traverse these trees. That is, if you give me the root of this tree, I have no way of traversing all the elements of the tree. The closest I can come to doing that, if I want to enumerate all of the elements in one of my sets, the closest I can come to doing that is iterating over my entire universe of elements and just asking the question, which of these elements have D as their representative, and then using that to reconstruct the complete set of elements in the set. So I can actually find all of the things in a set, but that is not a fast operation. That requires iterating over everything. But remember, our data structure doesn't involve that operation, so I don't care if that's slow. I want union to be fast, and I want find to be fast. So the data structure we've just come up with needs to have a name, and so if you look at an algorithms book, typically the term that's used is Disjoint Set Forest. And that makes sense to me. That's a good name for it, because it's a forest, a collection of trees, that represents the disjoint set data structure. Okay, that all said, it turns out that most people, me included, so later in this lecture I am going to do this, they just call this data structure a union find structure. That's it. Now, that's sort of weird, because isn't union find a description of the disjoint set structure in an abstract sense? There are lots of implementations of data structures that allow union and find. That's absolutely true. What we're going to discover, though, is that this data structure, the disjoint set forest, is so good at union and find operations that there is no competition. It leaves any possible competitor in the dust. There is basically nothing you could come up with that would be faster than a disjoint set forest, and it's not even close. Which means anytime somebody wants disjoint sets with union and find, that is the union and find operations, they're just going to use this. And so this data structure is so ubiquitous for this application that we've just begun to conflate it with the application. And I even do that. I'm usually quite precise about this sort of thing, but you've got to sort of take the temperature of the room in cases like this. In this lecture and in the next one, I'm going to talk about a union find structure, and I'm referring to a disjoint set forest. Sometimes I do make the distinction, but often in conversation, I just call it a union find structure. It is so good at this task that it has a monopoly as far as I'm concerned. All right, let's talk about the find operation. So the find operation in a disjoint set forest starts at some node. So you give me some node and you want to know its representative. So let's say you want the representative for node H. I just traverse upwards until I get to the root of that tree, and then that is my representative. And let's take a look at the union operation. So suppose I call union on C and E. So there's C and there's E. And notice that C and E are buried in the bottom of their respective trees, because of course I can call union on any two elements I want. Now the effect I want of this is for these things, these two sets, to become one big set. So the union operation has two steps. The first step is run a find operation on each of the two elements. In other words, starting at element C and element E, run the find operation to find the root of the respective trees. Okay, so now I'm working with the tree rooted at B and the tree rooted at D. That's the result of step 1. Okay, step 2 is to join those two trees together. Now it seems obvious here that what I sort of want to do is make B a child of D, but I don't have to do that. I could make D a child of B, because all I want is to ensure that when I'm done, if I do a find operation at any element in either of those two trees, that they both have the same representative at this point. Anything in either tree is now represented by the same thing. But it does feel natural, given that this tree is already pretty tall, to tether it so that B becomes a subtree of the larger tree. And the reason why that makes sense to me is, notice how when I'm done, so I started out with the taller tree here has height 2, so H equals 2. If I were to make this tree a subtree of B, then the resulting big tree would have height 3, because I've basically pushed this tree down by one level. On the other hand, if I make B a subtree of D, notice how the height of the resulting tree is still 2, because this tree was short, and so adding it underneath D doesn't really change anything. It sort of blends right in. And that seems to make sense. We already know, we're sort of attuned to this idea that keeping the height of the tree low is a good idea in trees. And we've already seen evidence that the height of the tree is going to play into the running time of operations. So we're going to encode that into our union operation. When I perform a union, I'm going to make the smaller tree, the one with the fewest elements, not necessarily the smallest height, but the fewest elements, I'm going to make the smaller tree a subtree of the larger tree. And that's step 2. Join the two trees by making the smaller tree a subtree of the larger tree. In other words, set the parent pointer of the root of the smaller tree to be the root of the larger tree. One thing you have to observe here, though, is that requires me to keep some information about how big each tree is. And when I say smaller tree, I mean number of elements. So the way we would do that in practice is we just tag each node of our tree with the total size of the subtree below it. So if we go back to our initial state here, we would say element M is the root of a subtree of size 1. It contains 1 node. So is element L, so is element C. Element B is the root of a subtree that contains 4 nodes. That's all of this stuff. And then similarly, let's see, element K, element H, those are subtrees of 1. Elements A and E are subtrees of 2. Element J is a subtree of 1. And then element D is a subtree of, it's got underneath it, let's see, 2, 4, 5, 6 things, including D. Now, we don't compute this every time we need it because, in fact, we can't. If I hand you a node and say, could you tell me how many things are below this, you can see that's actually impossible. I have no way of traversing the tree. Instead, what I do to keep that information current is I update it every time the tree changes. And the tree only changes as a result of a union operation. So what I would do here is when I perform the merge, notice that after, okay, let's redraw that. Notice that after the merge, this subtree still has size 4. The only thing that's actually changed is the size of the subtree rooted at D. So all I do is I set it to be size 10. I just add in the size of the thing I merged in. And in so doing, I'm actually able to keep the size numbers current after any merge in constant time. All I do is add in the size of the subtree that you stick below it. Okay, so when I perform a merge, I join the trees by making the smaller tree a subtree of the larger tree. Okay, we'll do another union here. Let's perform union B and I. Now, step 1 is find the representative for each of those nodes. Okay, well, for B, the representative is going to be D up here. And for I, well, actually, I is already the root of its tree, so that's easy. Okay, so I have that, and now I make the smaller tree a subtree of the larger tree. So I would set the parent pointer on I to be equal to D. There we go. And now, of course, you can see I actually have only one set in my entire collection now. And what's interesting about this is that means that the collection of sets can never change again. Although the structures of trees might change, and I'll come back to that in a while, once everything is in one big set, every union operation I could perform has no effect because I only have one big set. But that's just a consequence of the way we've defined the structure. The data structure is hyper-specialized, and so it does get into cases where it sort of becomes useless. But that's fine because I guess by this point it must have already done its job. All right, so as I've said already, the find operation walks upwards in the tree, which means the running time of find is big theta of h in the worst case, where h is the height of the tree containing the thing you are searching for. If we expand this out to talk about the worst case running time for any element, so if I think of what's the worst case running time of find in general, it's going to be big theta of h, where h is the height of the largest or the tallest tree in the forest. That is, if I'm lucky, I might do find on a tree that's short, but if I'm unlucky, I might do find on a tree that's very tall. So big theta of h on the tree that is the tallest among all the trees that represent any set in the collection. Now, the union operation, if we think about it, so step 1 of the union operation is go and find the representative for each of the two elements. Go find the representative for U, go find the representative for V. That's a find operation. Find the root of the tree containing those two things. Which means, because each find operation is big theta of H, where H is the height of the tallest tree, that the union operation, because once I've found the two representatives, let's go find a union operation here. So once I've found the two representatives, the actual union itself, the merge, is just setting a pointer. That's constant time, and we'll see that in the pseudocode in a minute as well. And then updating the size information, all that's constant. So the time of union is actually also going to be big theta of h. It's going to be 2 find operations plus some constant time stuff. And that means union itself is also just big theta of h, where h is the height of the largest tree being unioned, or in general, for an arbitrary union operation, the height of the tallest tree in the collection. So here's some pseudocode. And I love this pseudocode. I think this is an example of a data structure. This is such a simple, elegant data structure. One of the only reasons we couldn't cover this structure first, because this might be a good introductory data structure, given how simple it is. The issue is the analysis becomes very strange. That is, there are some aspects of this analysis that take us down a weird rabbit hole into complexity results that we were not expecting to see. And I will take your memory back to that picture of the Earth that I showed you at the beginning of the lecture. That will factor into our analysis of this later. So it's a very elegant data structure, and therefore a sort of nice breather topic if we need a breather from graph algorithms. So here's my find procedure. This one's iterative, and I think it's quite beautiful. We could write it recursively and would also be very beautiful. We're going to see a recursive version of find in about 20 slides or so. Okay, so the way find works is I give you some node in the disjoint set forest, and then I just walk up the tree until the parent is a null pointer, at which point I'm looking at the root of the tree, and then I return that. The add operation, which isn't really very important to us, that is, it's not that exciting, but we do need to have it, creates a new node, sets the element in that node to be the element that you provided, sets the parent to be nothing, and then sets the size associated with that node to be 1. The idea behind the add operation is it creates a new set containing one element, which is the new element you have created. If you want this element to be in some other set, well, then you have to perform a union operation on it afterwards. So to create a set of size 1, we just create a single node by itself as the root of its own tree, and then tag it as having size 1. And then finally, we have the union operation. Okay, so the union operation says first, you give me 2 nodes and say, merge the sets containing these 2 nodes. So my first step is go find the root of those 2 trees. Find the representative of each of those 2 sets. My next step is to check whether they're actually the same thing. So in other words, if I have a situation like this, there's A, and then somewhere down here, there's B. If I say merge, if I do a union operation on A and B, well, I'm actually merging a set with itself here, which doesn't really require any work whatsoever. So if I discover, once I've found the root, so of course the representative of A and the representative of B are both the same thing, if those representatives are literally identical, if they are the same thing, well then my merge is over. I'm already done. The set has already been merged with itself, so I just return. Otherwise, as of line 7, I assume that I'm merging 2 distinct sets together, in which case I look at their size. So if r1.size is smaller than r2.size, well, that means that r2 is going to become the root of the big set. That is, R2 is the representative of the larger of the 2 things. So R1.parent equals R2, and I update R2.size to account for all the nodes I just added beneath it, the nodes in the subtree rooted at R1. And then conversely, if R1 is the larger tree, I just do the same thing just with everything flipped. That is to say, I make R2 the child of R1. And so, I mean, this shouldn't require too much extra explanation there. So notice how, of course, as I've already mentioned, to allow the union operation to know which subtree is larger, which turns out to be critical. So the reason we're doing that is not just because it feels right, it's also because our analysis is going to demand that. That is going to be the way that we get the running time bound that we need. To allow the union operation to get that size without doing a bunch of extra work, we just maintain that information as part of each node object, and we just make sure we keep it updated as the tree gets modified. And one of the reasons this is so nice, like one of the reasons it's so easy to do this modification is the data structure is so specialized that we know the only time the tree gets modified, besides when I first create a single node, is when I do a union operation. So I can ensure that the sizes are kept updated every time I perform a union operation. All right, so our main running time bound that we need, and what I mean by need there is we're going to use union find structures, disjoint set forests, in the next lecture to talk about a particular other algorithm, which needs a disjoint set forest as to perform certain operations quickly. For the sake of making that algorithm fast, or demonstrating that algorithm fast, what I want to show is that both union and find are definitely log n if my universe has size n. This theorem actually states something a little bit more strict. It says if the tree contains k elements, and k could be less than n, the height of the tree is at most log of k. So of course that means that the height of any tree has to be less than or equal to log of n, which in turn means that if I run union or find on any collection of trees in the forest, that it will have log n performance. Okay, so by proving this, which I will walk through the complete proof of, we will have demonstrated that this data structure is fast enough that it can make the algorithm we're going to see in the next lecture as fast as we want it to be, to demonstrate that it's a very fast algorithm. However, we're not actually done with the analysis as far as union find structures go. This is the thing we're going to write a proof of. I want to come back later and talk about a quick tweak to the data structure that results in both union and find having developing a running time that is so incredibly fast that it's going to require a whole bunch of extra definitions just to define it. That is, it turns, as I said earlier, the disjoint set forest is really good at its job. And the result we are proving now is actually a pretty loose bound. It turns out that we can expect way better performance than log n. Okay, so my proof is going to be the proof that each of my trees has height. If the tree has k elements, height at most log k. My proof is going to be by induction on the number of union operations performed so far, because only a union operation actually modifies a tree. Now, what's sort of neat about this proof is that although I have my induction variable being the number of union operations I have performed, nowhere in my induction step do I actually use that number. I don't actually use how many operations have been performed. I just use that as my induction variable as a nice way to keep things regimented. That is, to I guess, methodically progress through each union operation. So it's a sort of unusual proof in that sense. It's a completely valid way of writing a proof. It's just interesting to see a case where an induction step where you use your hypothesis, but you never actually use your induction variable directly. Okay, so the basis is when 0 union operations have been performed, the only possible trees are single nodes. Okay, well, that's pretty easy because a single node has, a tree with one node has height 0, and 0 happens to be log base 2 of 1, which is the number of nodes in the tree, so the theorem holds. Great. And this is the reason I use the number of union operations executed as my induction variable, because it's very easy to assert a basis under those circumstances. All right, now here's my induction hypothesis. Suppose that after I've done m union operations, for some value of m greater than or equal to 0, the height of a tree that contains k elements has height less than or equal to log base 2 of k. So the height of any tree in the collection is at most log of the number of elements in that tree. So my induction hypothesis is suppose that that statement holds after some number m union operations. And my induction step will be now consider the next union operation up. So union operation number m plus 1. So I'm doing one more union. Who cares what specifically I'm merging with what else? This is now the m plus first union operation I have done overall. Let's let T1 and T2 be the trees that I'm merging at that step. Okay, so it's going to break into a few cases. Let's just wipe out one obvious case at the beginning. I've actually called this case 0 because I regard it with a certain amount of derision. So case 0 is, what if you are merging the same tree with itself? I mean, in other words, if we had that case I drew a minute ago where we've got this tree here, and I called union of A and B. Well, very clearly, that does nothing. So if the induction hypothesis held to all trees at the beginning of this merge, it will clearly hold at the end of this merge. I actually didn't have this case in there originally, and at the last minute, this is the last thing I added to this lecture, I added this in because I decided, okay, technically this is a case. You can actually merge a tree with itself, and so the proof should at least acknowledge this, and it's doing this. So it says, okay, if T1 and T2 are the same tree, if you are merging a tree with itself, then nothing changes, which means because we know that the hypothesis applies to every tree at the beginning of this merge step, because I changed nothing, the hypothesis still applies after this merge step, and therefore the theorem holds for merge number m plus 1. Great, okay, that's case 0. That's a pretty obvious case. We didn't really have to do any real work to prove it, but there it is, just in case we need it. Okay, the other two cases are non-trivial, and they are basically case 1 is the case where the two trees have a different size from each other, and case 2 is the case where the two trees have the same size. Now in case 1, let's say that T1 and T2 contain different numbers of elements. Now case 1 is distinct from case 2 because when the two trees have a different size, we actually know in advance exactly how they will be merged, because the smaller tree gets merged into the larger tree. So for notational reasons, let's define some things. So let's let K1 be the number of elements in T1, and let K2 be the number of elements in T2. Notice that I have named my trees effectively arbitrarily. I just said let the two trees be called T1 and T2. And nothing I've said so far has pinned down any specific details about those trees besides that they have a different number of elements. So without loss of generality, because we know one tree is larger than the other, let's say that T1 is the larger tree. In other words, go find me the larger of the two trees and name that one T1. You have to be careful when we say this because maybe I'm stepping on my own toes, but here I have done nothing else to distinguish these two trees. I say they have different numbers of elements, and I am now choosing to label the larger one T1, just so it's easier to talk about it. That way I don't have to do two extra cases, one where T1 is large, one where T1 is small. So we're going to assume that T1 is the larger of the two trees, and therefore that K1, the number of elements in T1, is greater than K2, which is the number of elements in T2. What we know based on that assumption is that the merge procedure will merge T2 to become a subtree of T1. Okay, so now case 1 breaks into two subcases. Case 1, let's see. Well, I guess I should talk about this before I talk about case 1a. So by the induction hypothesis, we know that I have T1 here, which contains K1 elements. By the hypothesis, the height of T1 is at most this number. So it could be less, but it's at most log base 2 of K1. Similarly, the height of T2, which has K2 elements, is at most this number. The union operation always makes the smaller tree a subtree of the larger tree, which means T2 becomes the subtree of T1, and after I'm done, the resulting tree contains K1 plus K2 elements. And what's significant about this is our goal in this proof, in this induction step, is to show that once I am done the merge, no matter how it happens, once I'm done the merge, the height is less than or equal to this, log of K1 plus K2. All right, case 1a. So case 1a is the case I mentioned earlier where we had a really tall tree, so a tree like this, and then let's make sure at least one node has 3 children. There we go. I have a really tall tree, and I'm merging it with a really short tree. So in this case, notice how if I add the short tree as a child of the tall tree, nothing changes about the height of the taller tree because the short tree just gets absorbed into the taller tree. That's case 1a. So we can phrase that formally. If log base 2 of k1, that is the maximum possible height of t1, is greater than or equal to the maximum height of t2 plus 1. So where's that plus 1 coming from? Well, the idea is the depth of the lowest level of t2, once I've combined the two trees together, will just be the height of t2 going in plus 1, because I've added it one level below the root of t1. Okay, so the height of the t2 half of the diagram is this thing. If the height of t1 was already bigger than that number, well, that means this sort of gets absorbed into the middle of t1, so nothing changes. So I didn't actually increase the height of t1 by doing the merge, which means the height of the resulting tree is this, the height of t1. And of course, the height of t1 by itself, log of k1, is definitely less than or equal to log of k1 plus k2. And so I now have a tree whose total height is log of k1, and which contains this number of elements, and so the theorem holds. Okay, so case 1a is taken care of. Now, case 2 is the situation where even though T2 had fewer elements than T1, they had a similar height. And that's the situation where log base 2 of K1, so once I've adjusted the height of T2, so of course T2's height is log base 2 of K2. But once I've put them together, so that is T2 is now a subtree of K1, if I look at the total distance from the root of the tree to the bottom of K2, it'll be this number here. So suppose that my height of T1 going into this was less than that. In other words, the height of T1 was less than the new height of the T2 half of the diagram. Okay, well that means that the total height of the tree that I end up with is now this, log base 2 of K2 all plus 1. Okay, so I'm going to show that this is still good. But to do this, I have to leverage what I know about T1 and T2. So first observe that we know that K1 is greater than K2 because we defined K1 or T1 to be the larger tree. So K1 is greater than K2. And that means if I think about, so K2, well, 2K2 is equal to K2 plus K2. And we know that K1 is greater than K2, which means that if I say that K2 plus K2 is less than or equal to K1 plus K2, that's, I don't know if I needed to expand that out, but there it is. So because K1 is greater than K2, 2 times K2 is less than or equal to K1 plus K2. So keep that in mind for the next slide. Okay, so the height of the new tree is this. It's log base 2 of K2 all plus 1. We saw that on this slide here. And that is equal to 2 times log of K2, or sorry, log of 2 times K2. That is because of logarithm shenanigans. So if I use the law of logarithms on this and I observe, well, yeah, so we've done this before. I often over-explain the use of logarithms. We know how logarithms work. So log base 2 of K2 all plus 1. If I fold those logarithms into one single thing, it actually ends up being log base 2 of 2 times K2. By the previous slide, 2 times K2 is less than or equal to K1 plus K2, and that means that we have what we need. So the theorem holds. Okay, so in case 1, in both of the possible breakdowns of case 1, the theorem held. So there was the case where T2 was just sort of folded directly into T1, the theorem held. The case where T2 ended up drooping a little bit below T1, the theorem held. Okay, so that's case 1 all taken care of. Now what about case 2? In case 2, that's the one where T1 and T2 contain the same number of elements. So in case 1, we knew that one tree was smaller, and so we knew which direction the merge would go. Suppose that both trees are identical in size. So T1 and T2 have the same number of elements. And that, of course, means that the union operation could merge them in either order. In other words, I mean, we could do it like this, or we could do it like this, because the only rule we define for the union operation is simply that the smaller tree becomes a subtree of the larger one. So when there's a tie, I guess it could go either way. Again, just to clean up things, to make it easier for us to talk about, we know that the union operation makes one of them a subtree of the other, and I've done nothing else to distinguish them so far. They have the same number of elements, so let's decide that T1 becomes the new root, and T2 becomes a subtree of T1. All right. The resulting tree, once I'm done, well, both trees coming in had k elements. The resulting tree has 2k elements. And the height of the tree, well, let's think about this. So we know by the induction hypothesis that both trees going in, they had k elements, so they had height at most log base 2 of k. which means once I make T2 a subtree of T1, well, the height of T2 by itself is log base 2 of k. That's a pretty bad k. Log base 2 of k. So once I attach it below the root of T1, the total height will be log base 2 of k all plus 1 at most. So I guess I haven't been too clear about that, or as clear as I want it to be. But remember that the hypothesis doesn't tell me the height is exactly log base 2 of k. It tells me the height is at most log base 2 of k. It could be shorter, in which case things are even easier for me. Okay, so the resulting height is log base 2 of k plus 1, and then as I said earlier, so of course I will actually write it out. I just can't stand not fully explaining the logarithms for some reason. This is log base 2 of 2, and then by the law of logarithms, that ends up just folding together to be log base 2 of 2k, and I realized that what I ended up with, therefore, is a tree that contains 2k nodes, and whose height is at most this number, which is equal to log base 2 of 2k, and that's what I want. There are this number of nodes, and the height is log of that, so the theorem holds. Okay, what can I say about all that? Well, cases 1 and 2, I didn't even bother giving case 0 a mention here. Cases 1 and 2 cover all possible merge configurations, so merges that actually happen, and that means that the theorem holds after merge step n plus 1. There is no way a merge could occur that doesn't fall into one of cases 1 or 2, unless it's a trivial merge that falls into case 0, which we already showed would still be fine. So we've shown that after n plus 1 merges, everything's still good and the theorem still holds, and therefore by induction, the theorem holds for any number of merges. So after any number of union operations, the height of each of the trees is at most log of the number of elements in that tree. And that is sufficient for us to assert that if I have a universe of n elements, both my union and find operations are, big O, are big O of log n in the worst case. Because notice that in that last proof, I never was able to show that the trees actually would have height log n. That is to say, they could, and we can discuss that separately. We're going to see in a minute that with a couple of tweaks, we can actually show that this definitely isn't a very tight bound on the running time of the algorithm. So although I can construct disjoint set forests that do actually attain log n performance, I'm stating this here almost as a provocative gesture because I want it to be clear that what I've shown is that certainly this is a fast data structure. It gives us log n performance for union and find. I don't want to bother showing that it actually is log n in the worst case because I'm about to refine it in such a way that the running time becomes ridiculously fast. So based on what we've already done, which is performing union operations by always merging the smaller tree to be a subtree of the larger one, and we saw in the proof that that was sort of critical. If we could make a large tree a subtree of a small tree, that could result in trees getting pretty tall. But because I always make the I always make the small tree a subtree of the large one, the tree height is manageable as the number of nodes increases. That is, although the tree's heights do increase, the number of nodes increases fast enough that we can still bound the height by log of the number of nodes. But there's one more optimization I want to introduce, and we're not going to write any proofs of the resulting running time, and I think you'll see why I choose not to do that once we get there. So we're talking about these arbitrary trees. There is no limit on the number of children a node can have because a node doesn't need to keep track of all of its children. It has as many children as choose to point to it. And depending on the specific order that I do union operations, I could end up with perhaps disjoint set forests that actually look like this. In certain, well, actually not entirely, not really long chains, but ones that are a little bit more spindly, or I could end up with disjoint set forests that look like this. The thing I stopped myself from doing there is I wouldn't actually get a situation like this showing up. If you think about this, think about the set of merges that would have to happen to do this. Eventually, you're going to get a situation where you have to begin merging against the root because that requirement that when you merge the smaller tree into the larger one would take over. So we don't have to worry about the weird like glorified linked list we get with like the worst case of a binary search tree. So we just proved that, so that's something we can accept by now. But in any event, based on the order of merges, I could get trees that have a variety of different structures, but the maximum number of children of a node is really bounded only by the number of nodes available. So, for example, if all of the nodes of my forest are in the same tree, then it's possible of the root of that tree to just have n-1 children. Every other node in the collection is a child of that root. Now, of course, it's obvious that if the trees are all short, that's good for everybody. That is, every operation gets faster if the tree is short. And so I can't help but wondering whether maybe, currently the only time the tree gets modified is during a union, but I can't help but wonder if maybe a bit of extra work could allow me to build in some shortcuts and make trees get shorter and shorter the more I use them. notice that this tree here, so if I think about this set represented by C, I could redraw this. I could say there's C, and then I could just make every other node a direct child of C. So in fact, any collection of nodes can be represented by a tree of height 1. It's just a matter of, I guess, luck of the draw, whether I end up with a tree of height 1 like this, or I end up with, in this case, a tree of height 2. So here's an idea. Every time I use a node, so let's say I run a find operation on F, let's just push it upwards in the tree. If I have to traverse this path anyway, why don't I also modify it so that there's a shortcut? Every time I have to traverse F, let's just set F to point directly to the root so that next time I use F, the path is shorter. The union operation wouldn't do this. So the union operation only accesses root nodes. So the only, well, that's sort of false. That is, in the union operation, I call the find operation. What I mean is that when I say directly here is that as far as things the union operation directly touches, it's only going to be the roots. So the only operation that actually sees nodes lower down in the tree is the find operation. And the find operation may have to traverse a sort of long path. I might start pretty low down and go all the way up to the root. What I'm suggesting is, as I do that, so because I know that once, to figure out the representative for that node there, I have to go all the way to the root. All I'm suggesting is, once you've found the root, go back down and just build a shortcut from every node directly to the root. So rearrange the tree to make it shorter every time you have to see a node. That means that over time, you end up with a configuration more like this, where the next time you do a find operation on F, it ends up being blazingly fast. Because if everything is at level 1, then that means a find operation for something at level 1 is basically constant time. I just walk up by one step. The number of steps I walk up isn't really governed by the number of items in the tree at that point. So in this case, the example of F here, when I run a find operation on node F, I traverse both F and E. And in general, if the chain ran further down, if I have to start down here, I have to walk through every node on the way from there to the root. What I'm suggesting is every time you walk a path from a node to the root, you set the pointer from every node along that path, not just the one you started with, but every other node to point directly to the root. So now I've built a whole bunch of shortcuts into my tree. This is called path compression because, of course, we're shortening the paths in the tree. And it results, once a find operation has been run on a particular node, at every node encountered by that find operation becoming a direct children of the root, and therefore all future find operations at that node being essentially constant. And I shouldn't even say essentially. They are physically constant time, because I'm walking up by one step and then I'm stopping. The only part of this that wasn't constant is the part where in the initial traversal, when I start at F, when it's lower in the tree, building the shortcuts, of course, isn't constant time. So once I've done a find operation at every single node, that means I can expect every node to be at depth 1, and therefore every future find operation to be constant. So here is pseudocode for a modified find that does this. It's only necessary to modify the find operation to achieve path compression, because the union operation, if path compression occurs during a union, that just is because it's happening during the find step that occurs as the first part of union. Okay, so here is a recursive implementation of find. I give you a node and I say, give me its representative. Well, if the parent of that node is nothing, then I guess you already are at the root, so your representative is the node itself. Otherwise, what we'll do, so let's just draw ourselves a tree to work with here. We've got something like this. So I am at this node here, and I know that this is not the root of the tree. So I recursively find the representative of the parent of this node. And we know that the find operation always returns the root of the tree. So recursively, what I will eventually get from this recursive call is the root of the tree. And so I'm at this node at the bottom here, and I call the find operation on my parent to get the root of the tree. When it sends back the root of the tree, I set my parent to be the root directly. So I build the shortcut. And then I return my new parent, which is also going to be the root. So I return the correct representative. And because I've done this recursively, even if I had to walk through tons of different layers of the tree to get that done, so I make the recursive call from here, okay? Well, I recursively find the parent of this thing, okay, but I'm not done yet. I recursively find the parent of this thing, whatever. I recursively find the parent of this thing, okay, there's no parent of this thing, this is the root. So I return a pointer to this thing down to this level. And then it sets its own parent to be the root, which is actually a no-op because it was already a direct child of the root. I go down here and I return the root to this level of recursion, and I set its parent to be the root. I then return the root to this level of recursion and set its parent to be the root. And notice that that was a big mess, but once I was done, all of the nodes I saw are now direct children of the root, and the next find operation I do will be constant. So I've teased this already several times in the lecture, but when I use path compression, so when I add this find operation on top of the pseudocode we've already seen, the union and find operations become nearly constant. And you know me well enough to know that when I say nearly constant in a formal setting like this, I better be able to back it up. Because sure, you could argue any fast algorithm is nearly constant. I mean, for example, if I can give you an algorithm that is log of log n, well, that might be nearly constant because log n is small, so log n is even smaller. No, but that's not nearly constant in my books. Log n is definitely a function that has a non-trivial rate of growth. It is not a constant function. A constant function is a constant. So I use this term very sparingly. I actually agonized over whether to say it. That's why I'm giving this long disclaimer. I decided it was warranted for reasons that will become clear in a minute. So the running time, once I add this find operation with path compression, if I consider the amortized running time, that's analysis we are not going to do, but I'll talk about that in a few minutes. If I consider the amortized running time of a find or union operation, it is faster than log n. It's faster than log of log n. It's faster than log of log n. In fact, you can put a whole ton of logs together before you actually get the running time we're talking about. In fact, the number of logs you have to use depends on how big n is. So it isn't actually a function we can express in terms of logs. Okay, so what do? I want to talk about a running time expression that is something very bizarre. And to do that, I'm going to start in the opposite place. I'm going to define something called the Ackermann function. Now, a weird technical aside here, there actually are multiple functions that purport to be the Ackermann function. It seems to be some weird tradition in this neck of the woods to call this the Ackermann function, even though technically it's just an Ackermann function. There are lots of different formulations of this function, and they are distinct from each other. Speaking of which, if you go look at an algorithms textbook for the Ackermann function, and if you look up union find, that's probably where it'll be defined for the first time. Every book I have looked at, so I've spent the last few months with this huge stack of algorithms books sitting next to me, all of them have a different idea of what the Ackermann function is. So why did I choose this one here? This one here is actually, I traced it back into a book about computability, so this ancient textbook about computability that we don't need for this course. Now, computability, for those interested, is the study of what can and cannot be evaluated by a computer. And the Ackermann function comes to us from that subdiscipline. The reason I chose this definition, which, by the way, if you look up Ackermann function on Wikipedia, you get a far more accessible treatment of the subject than anything in the algorithms books I've seen, and that includes this definition among a few others. The reason I chose this definition is because this formulation of the Ackermann function, or this version of an Ackermann function, is an ordinary-looking recurrence. That is, we have seen recurrences that look like this. It is certainly rather odd that it includes this nested recursive call, but we know how to evaluate this kind of recurrence. You could write code to evaluate that. And by the way, good luck. Go ahead and try and implement this recurrence in Python and see how many values you can evaluate. More on that in a second. So I chose this representation because it's very important to me that we understand that although the Ackermann function, and I don't exaggerate when I say this, although the Ackermann function is inconceivably strange, it is really weird, to the point that I hope you're not watching this late at night because it's really weird. Although the Ackermann function is really weird, it is clearly something that is tangible in our domain. That is, it is representable by an ordinary-looking recurrence. And if you stare at it for a bit, although it's got a strange configuration of base cases, you can conclude that indeed, for any value of m and n that are non-negative, you can compute this function. Like, there is a way of determining the result. Now, whether your computer can do it is a different question. Okay, so let's take a look at a table of values of the Ackermann function. And as I said, when I say the Ackermann function, I mean this thing, not any other definition somebody else has given. Although definitions vary, they all have the same basic trend, which is if you look at a table of values, the table starts out rather civilized. Row 0 just counts up in steps of 1. Row 1, as far as we can tell from this point of view, is counting up in steps of 1 as well, frankly. Row 2 is counting up in steps of, I don't know, 2 or something. If we go down the columns, we get 2, 3, 5, 13. Okay, fair enough. Oh, that's a sort of a big number. That's weird. But notice as I progress diagonally through the table, the function explodes. Explode isn't even the right word. The function attains values so large that they defy our human sense of scale. And what's even stranger and even more bizarre about this is that I can't show you a bigger table. I can't. Not that it won't fit on my slide, but literally, I don't know how to represent the value that goes there. I especially don't know how to represent the value that goes here, A55. That is, if I wanted to tell you about A55, if I wanted to write it into the table, I would first have to define specialized mathematical notation for extremely large numbers. And keep in mind, A44 is certainly doesn't have anything to be worried about in that domain either. A44 is an absolutely outrageously large number. A55 is so big that none of the notation that we know would be sufficient to describe it. Not just that it's a big number, but literally we don't have notation. And even if I define specialized notation to refer to large numbers, that notation would break down at, I don't know, like A77. So there is notation out there. You can look this up. If you look up Ackermann function on Wikipedia, it does have a good description of this. There is notation out there that allows us to refer to extremely large numbers in some relatively compact form. Even that notation becomes useless with relatively small values of the Ackermann function, relatively small arguments of the Ackermann function. If I begin reasoning about A1212, there is no notation I can even think of, no notation we can conceive of that could truly allow us to understand the scale of that number. Okay, so first off, what is this doing in the middle of this lecture? What are we doing talking about this function that grows incredibly quickly? So you can see, as I said, if we skim across row 4 of the table, and as I said, things get even worse really quickly when I hit row 5, the values grow absolutely astronomically between entries of my table. The reason the Ackermann function plays into this is that the Ackermann function was famous for a different reason. That is, it was used originally to prove a result about computability, an extremely obscure result by our standards, so something you'd see in a graduate level computability course probably, or a graduate level maybe computational complexity course. However, it became famous because people that knew about computability knew about it, and it became a sort of reference point. Whenever somebody wanted to talk about a function that grew incredibly fast with an outrageously high rate of growth, they would use the Ackermann function for a sense of scale. So consider the last time you had a height described to you in terms of the CN tower. So you could be told this building is twice as tall as the CN tower or something. I don't actually know if a building like that exists, but or this, radio antenna, or this mountain is twice as tall as the CN tower, or this distance is like 2 CN towers put end to end. Or for example, seeing a volume of liquid or an area referred to in terms of Olympic-sized swimming pools. People don't actually use Olympic-sized swimming pools as units of measurement, but it does help our human brains understand the sense of scale. And the Ackermann function has been adopted, I guess, as a way of getting a sense of scale when you're talking about functions that grow outrageously quickly. If you can characterize them with their relationship to the Ackermann function, then people that know what that means get some idea what you're talking about. Okay, so speaking of that, as I prepared these slides, I realized that I actually can't do a good job. Like, even what I just said doesn't do a good enough job at explaining just how big these numbers are. So the biggest number I'm able to show, that is the biggest one I have notation for, is this. This looks like a very large number. 2 to the 2 to the 2 to the, well, actually, this number here is what? Like 2 to the 16, 2 to the, this is, yeah, 2 to the 16. So 2 to the 2 to the 2 to the 2, and then I go up with a tower of 2s that's 16 more. So just more and more of these things. That's a big number, isn't it? Yes, it's a big number, but you don't even know the beginning of that. Like, just to be clear, I think we've reached a point where our human ability to understand scale sort of breaks. And that brings me back to something I talked about at the beginning. Let's look at some photographs. Let's diffuse the situation. Here's a famous photograph called Earthrise. It was taken as part of the Apollo 8 mission on December 24th, 1968. Okay, and there's the Earth. We're all in this photo. Actually, none of us that were... I was not born at that time, and if you were not either, I suppose you're not in this photo. That is the entirety of the planet Earth. And it's really hard to understand the sense of scale involved here. Think about the distance involved for this to show up at this scale in this photograph. It defies my human brain's sense of scale to see that, to how far away we have to be for an object of the size of the Earth to appear this small. That's ridiculous. And I hoped by showing this to illustrate exactly how our brains treat a sense of scale. We as mathematicians can talk about large things. We can talk about large distances or massive numbers or massive senses of scale, and we can think about them, we can reason about them academically, but do we really know how big those numbers are? So here is a picture of the Earth that shows, you can see the Earth. It's made out in this photograph. And then here's the photo I showed at the beginning, the pale blue dot. And the Earth shows up there. You can actually, strangely, it's sort of illuminated. You can see it there. It's one little dot in the photo. This photo was taken from a distance of 6 billion, so I'll just draw the zeros for the sake of dramatic effect, 6 billion kilometers away. That is the distance that light travels in 5.5 hours. And in this photo, the Earth is less than 1 pixel. Apparently, and you can look this up, I'll put a link in the video description, this is the pale blue dot photo. And I'll also link you to a monologue by Carl Sagan about this, because it's actually quite profound. It's actually quite existential. The Earth in this photo is 0.12 pixels in size. So not only is it just a dot, it's actually less than a dot at the resolution of this photograph. That is how far away the Earth is from the camera here. 5.5 light hours away. Everybody that ever lived and everything that they ever did took place on that tiny dot. Everything. Everything you can ever think of a human ever having done took place on 0.12 pixels from a distance of 5.5 light hours away. Imagine that distance. And now think about the fact that if you look up facts about interstellar space or about the universe, it is quite normal to talk about distances of light years, or of millions of light years, or billions of light years. This is the Earth from 5 hours away. And now think about a distance of light years. And I hope that helps you understand at least my concern about my brain's ability to understand scale. I can look at a number and say, yeah, that's a big number, but it's really hard to reason about scales that are this massive. Okay, so what are we doing talking about this photo in this lecture? So I brought up the Ackermann function as an example of a function that grows outrageously quickly. But that's not the point of our data structure. We were designing a data structure that's fast. I certainly wouldn't want to create an algorithm whose running time is the Ackermann function because I don't have that kind of time. Because the Ackermann function is a reference point for really fast rates of growth, we can define a sort of inverse function, although it is inverse in name only, so it should be a proper noun because it's just named the inverse Ackermann function. It's not a true inverse function. We can define a function that has an accordingly outrageously slow rate of growth. We'll call this function alpha, or inverse Ackermann of n. And there's lots of ways of defining this. I've defined a simple version that's sufficient for our purposes because we've already been philosophical enough today, and we've talked too much about big numbers. So the inverse Ackermann function is the minimum value of n such that a of n is greater than or equal to n. Now it's hard to make heads or tails of that, especially when the Ackermann function itself is so strange and bizarre. So I can give you a concrete point of reference. Because we know that a44 is this massive number, that means that alpha is going to be less than 4 for any value of n less than this. And so comfortably less than 4 for any value of n we are likely to encounter. And here is where I thought it was so important to talk about the scale of numbers. We look at this as people that deal with running times of 2 to the n sometimes and say, yeah, that's a big number. But that isn't even the beginning of it. So this number is so large that it's hard to even think of, to imagine a quantity that could be referred to by this number. That is, if we have a computer that consists of every atom in the observable universe, well, that's only about 10 to the 80 things. That's nowhere close to this number here. That's not even in the same, that's a speck. That's not even a speck compared to this number here. So what that means is that if you end up with an algorithm whose running time is proportional to alpha, to inverse Ackermann of n, then inverse Ackermann of n is going to be less than 4 for anything up to this value. And this value is so large that we can't even conceive of it. You don't have this amount of time. You don't have this amount of memory. You don't have this amount of matter in the entire, okay, I should be careful, the entire observable universe. And as I said, if we think about a photograph where Earth is a speck, that's 5 hours away by light. And we can talk about distances in the universe that are millions or billions of light years away. And I'm talking about how if we think about all of the matter in the observable universe, that is less atoms than this number by such huge orders of magnitude that it's not even close, that it's hard to even compare those two things. So that means if I have an algorithm whose running time is alpha of n, that algorithm is basically constant. Because frankly, we do have to acknowledge our human limitations here. For any problem that any human will ever encounter until we ascend to some higher plane of existence as the species, we can assume that alpha of n will be 4. We're not going to ever experience any input where the size of the input is bigger than or even close to this number, which means that although technically speaking, asymptotically, alpha of n is not constant. That is, if you go compute limits or something, you can show that alpha n is little omega of constant. The thing is, for all of our intents and purposes, for every use case we can think of an algorithm, alpha of n is a constant. So although we should be careful about the formal distinction, if we ever find an algorithm whose running time is less than this, then it's basically a constant time algorithm as far as we're concerned. Okay, so back to our discussion of disjoint set forests. It turns out, fact, so I'm not going to prove a theorem about this. I think you'll thank me for that. Although if you do want a proof of this fact, it can be found in a variety of algorithms textbooks, and there is a reasonably accessible one in one of the sources I've been using recently. I'll put a citation of that in the video description. So basically, if I perform some sequence of m operations on my disjoint set forest, so the m operations can be any combination of union and find in any order I want, the worst case running time of the whole sequence is big O of m times alpha. Now it's big O of m times alpha because, as I mentioned earlier, the Ackermann function itself is so synthetic, it would be very bizarre to find an algorithm other than the one that computes the Ackermann function that actually has a running time equal to the Ackermann function. All we're saying here is that the running time of those m operations is at most m times alpha of n. In other words, for our purposes, m times a constant. So if I then amortize that over the m operations, so if I'm doing m operations and the running time is this in the worst case, then that means the worst case running time of each operation individually, amortized over all of them, is just alpha of n. And as I said, that's essentially, for our purposes, a constant. Now, one last thing before I move on for the Ackermann function. I have to make sure I point this out. I mentioned that you're welcome to implement this recurrence because you can write code to evaluate this. Go ahead and do it. If you want to upset your Python interpreter or something, try doing that. You will find that you run out of memory very quickly. That is, we know these numbers because people have used specialized tools to come up with them. But even with variable precision arithmetic, good luck making your computer actually do this arithmetic. Because not only is the number large, the recursion sequence to compute these numbers is very complicated and will exhaust your computer's memory far quicker than it will actually get to any sort of result. Okay, so basically what we've shown here, or what I've said that can be proven elsewhere or in a higher level setting, is that the union and find operations on my disjoint set forest are so fast, if I use path compression, that they are effectively constant. That is, and I don't use that term lightly, they are effectively constant. They are bounded by a function that grows so slowly that at no example of human scale, or even human fathomable scale, no example the size of a universe or less, will they ever exceed 4 operations. Or a running time that is proportional to a constant times a constant, because alpha then grows so slowly that it is constant for our purposes as humans. Okay, so what does that tell us? Well, one thing we can observe is going way back to our original application where we were finding components of a graph. Well, first thing, and it shouldn't surprise us that we can do this, we can use a union-find structure. Notice that I'm calling it that now, because I think we've determined that disjoint set forests do have a monopoly. Their running time is so good, I can't expect to get any better than that, so I guess they get to own the idea of being a union-find structure from now on. So we can use disjoint set forests or union-find structures to compute components of graphs. And we actually end up with an extremely elegant algorithm for that. So what I do basically is I observe that if I already know the components of a graph, so suppose I have these two components here, and I want to add a new edge, what I'm really doing if I want to update the components is merging this component with this one. So that's great. If I already had the components stored as trees in my disjoint set forest, the merge operation I now know will be ridiculously fast. But I realized that I could just use that same insight to compute the components from the outset. That is, I could say, here's my graph of, let's say, I don't know, 7 vertices. And I know it has edges, but pretend at the moment that the graph has no edges whatsoever. Make a separate component for each vertex. And now, one by one, bring in the edges as if you're adding them to the graph. In other words, just merge components starting from each vertex being in its own component, go through all the edges and perform the corresponding merges. And when you're done, you should have in your union find structure a set corresponding to each component in the actual graph. So what I do is I first add each vertex to a set by itself. I then iterate over all of the edges and I perform a union operation. And then, and this is just for symmetry, because arguably if I want to know which component a vertex is in, I could just call find directly. But because I want to compare this to my DFS-based scheme, I will actually go through this extra step. If I want the mapping of vertices to component identifiers, I then go through each vertex. I make an array. I make some mapping. So for example, an array. I go through each vertex and then I run a find operation to get the representative for that component and store it in the array. I think the slides are going to do the same walkthrough I just did. Yes, there they are. And what I have now has the same effect as that DFS-based scheme that we saw in the last lecture and that I talked about at the beginning. And notice that if you contrast the two sets of pseudocode, this is really elegant. It's very simple. And although, yes, it's because it's farming out some operations to a data structure, we understand that data structure is not only simple, streamlined, and elegant, but also ridiculously fast. The total running time of the algorithm, okay, well, if we look at it, I call add operations over and over again. That would be proportional to the number of vertices. I then call union operations exactly this number of times. So I call one union operation per edge. And I'll also observe, look at how elegant this is. I iterate over all the edges once in order. I just go through all the edges exactly once and call union on them each time. I don't have to go through edges more than once. I don't see each edge from both endpoints. I just look at each edge once. And then, so the number of total union operations is this running time here, number of edges times the running time of a single union operation, which is at most inverse Ackermann, or alpha of n. And then I compute the representative by calling find on each vertex. So that would be number of vertices times inverse Ackermann of n. Okay, so my earlier DFS-based approach, as we know, is big theta of v plus e. So no funny business here. It actually is just linear in the number of vertices and edges. Notice that this clearly is asymptotically superior to this, because we know that inverse Ackermann is not a constant formally, and therefore this expression is asymptotically larger than this expression here. So that means if we use only asymptotic analysis, the DFS-based algorithm is faster. But I mentioned back when, ever since we've been using asymptotic analysis, I mentioned that the reason we've chosen it as a tool is it's the right compromise between giving us information about a problem and not giving us too much information or getting us bogged down in semantics. But with any choice like that, there are risks that there could be cases where you miss something. And certainly a case where we're talking about the Ackermann function and its inverse, which are really bizarre. I hope if you take nothing else from this lecture that you take away that the Ackermann function is really strange. If we're talking about those, it shouldn't surprise us that asymptotic notation might be betraying us a bit. That is, although it's true that if we think about this in an absolutely infinite sense, that there will come a point at which this linear expression here will be decisively smaller than this other semi-linear thing based on the inverse Ackermann function, that point happens so far in the future with such large values of n that it's irrelevant to us. It's so far away from us we can't even see it. And so I guess the question we should ask is this algorithm actually going to be faster? Because the difference seems to be, if we treat this thing as if these truly are constants, it looks as if we have a v plus e algorithm versus another v plus e algorithm. And I think this warrants an experiment. This actually warrants a timing experiment. Although timing experiments prove nothing, they do give us some perspective. And after all of the weird discussion we just had about the scale of numbers, I think we do need some perspective to ground us back down on planet Earth. One thing I observe about this DFS-based algorithm is that although it is linear time, it is complicated. There's a lot of machinery, a lot of recursive calls, a lot of iterating over lots of things, and that involves not just doing lots of stuff, which is constant time, so constant time overhead, but also wandering all over memory. That is, I have to wander through each vertex, versus this very clean breakdown where I iterate over all edges once, I iterate over all vertices twice, and that's all I do. So because the union find version is more streamlined, I think we should do an experiment. So I want to do an experiment on a bunch of different graphs, and for the sake of of having a cleaner outcome, what I'll do instead of just finding the components is I'll count the components. So to verify that my algorithms are getting the right answer, beyond looking at them theoretically, I will use variations on the algorithms I just showed, where instead of just listing the components in a table, they just return the total number of components. So here is the union find version of that. So I make a new union find structure, I add each vertex as its own set, I go through each edge and perform union operations, and then I go through every vertex and I look for all the vertices that are their own representative. And the idea here is what I'm doing is counting the number of roots of trees. So I just go through and I add 1 to my component count every time I see a vertex that is the root of its tree. And then I return that. Okay, so there's one way of counting components. It has the same asymptotic running time as the previous algorithm, but it's a bit cleaner as far as doing an experiment. Here is the equivalent version for DFS. Now, in the union find version, I could get out of having to have that table of component indices, but in this version I sort of can't, because I need the table of component indices for other purposes in DFS, for things like testing whether a vertex is visited. So if I get rid of the table and use some substitution, I'm getting a bit too far away from my earlier algorithm, so I'm going to leave the table in. So what I do is I basically just label the components as I was doing before, but then I return, so this variable component num at every step, it stores the index of the next component to create. So if I return that -1 at the end, that will be the total number of components. The running time of this is the same as the running time for the algorithm that finds components. And so now I have two algorithms that I can compare on some set of graphs as part of an experiment. As we know with timing experiments, we need to be aware of the details. And so I provided enough here to make it clear what I did. So this experiment can't be generalized overall because I'm randomly generating graphs and there could be bias in the way that I've generated them. I believe I've created an experimental methodology that is at least thorough enough that the performance difference that we see is meaningful. It doesn't mean that one algorithm is better than the other in general, or even that it's better than the other on a specific class of graphs, only that if I generate random graphs that are well distributed enough to represent some kind of random sample, that it does tell us something. It sort of helps us understand the differences between running times. So I generated a collection of 200 random graphs, and these were disconnected graphs. And the way I generated all 200 graphs was I considered various vertex counts between 10,000 and 100,000 in increments of 10,000. So in other words, n went from 10,000 to 20,000 to 30,000 and so on, up to 100,000. For every value of n, I chose a number of edges to add, and I chose various different edge counts. So for each value of n, I chose 4 different edge counts to try, and I modeled them as f times n, for f equal to 0.5, 1.0, 1.5, and 2.0. In other words, in the case where n is equal to 20,000, I would try values of m that would include 20,000 times 0.5 is 10,000, 20,000 times 1.0 is 20,000, 20,000 times 1.5 is 30,000, and 20,000 times 2.0 is 40,000. Okay, so I try all of those values of m. And then for every combination of n and m, so every pair of n and m values, I generated 5 random graphs. And the idea was I want to have multiple trials because, if for this value of n and this value of m, I don't want to have only one graph of that size because maybe I generate one that has certain weird pathological behavior. I generated 5 different graphs with the same number of edges and vertices so that I get hopefully a bit better of a sample of the graphs of that magnitude. Now, the number of components didn't play into my generation scheme, but of course it is relevant to this problem, so I'll give you some statistics about that. In my collection of 200 graphs, and I'll observe that there were 10 values of n, 5 different graphs per pair, and 4 values of m, so that would have been 200 in total. Over my collection of 200 graphs, the graph with the smallest number of components had 157 of them, and the graph with the largest number of components had 50,002. And that's a pretty good spread, although we could argue that maybe the DFS-based or union find algorithms have way different performance on graphs with like 2 components or something. So now we know how many components we're working with. Here's the results of the experiment. So if I go by number of vertices, now of course there were multiple graphs for each number of vertices. So what I've done here to make these line graphs is I've taken the data for each particular vertex count and averaged it, and then I've just plotted that average for the sake of the data being sort of clean, because it's mostly an experiment for the sake of understanding the algorithm versus proving some scientific conclusion. Notice that, so first, the timings I think are meaningful. That is, I trust that on the platform I was using, this resolution, 0.002 or 0.001 seconds, is high enough that I think the timers I was using were giving meaningful output, especially because I was using a lot of different graphs. And we can see that the DFS-based approach is decisively worse. That is, in general, if I look at the average running time across all graphs of a given number of vertices, it is very clearly worse and sort of diverges. Now, the progression doesn't look fully linear, although I believe it actually is. I think that these elbows we're seeing here are either platform-specific behavior. This is a hypothesis. I'm not guaranteeing this is the case. Or it's mostly just the fact that we've tried to connect points by a line. I think overall we're actually seeing a linear trend here. If these elbows are platform-specific behavior, that is, if performance seems to get slower at this point, at this inflection point, that could actually be caused by cache issues, which is something outside of our context. But it makes sense that of the two algorithms, DFS is more susceptible to caching issues because DFS is wandering all over memory, whereas the union-find-based approach iterates through all the edges once, which means that the number of cache misses might be less. That's all just a conjecture, but that's something that when I see a plot like this, one possible explanation. Although, as I said, I actually think it's a pretty much linear progression. And we see that the union-find-based approach is decisively faster. Now, if I aggregate data not by the number of vertices, but by the number of edges, I get this, which is a bit noisier. And the reason for the noise is because the number of edges and the number of vertices play into each other in a way that isn't entirely independent, because so I think this could just be bad experiment design. That is, I chose the number of edges based on the number of vertices at each step, which means that I don't necessarily have a completely independent distribution of edge counts by vertex counts. But we see, though, that overall, as the number of edges goes up, so does we see the same general relationship forming in running times, and I think it also is vaguely a linear progression. One thing that's neat here is that I'm not sure exactly what causes these bumps, because there's lots of different things that could be affecting this, but it's interesting to note that if there's something that makes this collection of graphs harder, that is felt in the union find algorithm as well. So it's not like we're hitting some particular worst case of DFS only here. It could be simply that because of the interaction between edges and vertex counts, there are some more difficult graphs that show up at that point. And that's worth considering. Another thing that's worth considering is any timing experiment that generates random inputs doesn't necessarily give you information about the worst case running time of the algorithm, because we're not generating worst case inputs here. We're just generating inputs. And so this should not be interpreted as a validation of a worst case result, but instead a way of understanding some perspective about expected running time and evidence that to the extent that that inverse Ackermann function seems to influence the running time of union find, that it doesn't make that much of a difference. That is, union find, by being so streamlined, is able to get better performance than the DFS-based solution. Okay, and one last plot, a completely useless one. I tried plotting the data by the number of components just to see what would happen, and it was sort of garbage, as you can see. So the data is really noisy and I would say pretty much worthless. But I mean, notice how, DFS is still coming in last, but that doesn't mean anything because the data, that is to say, we know already DFS seems to be slower, the DFS-based approach. In hindsight, I really wish I had tried BFS as well to see whether maybe the recursive infrastructure of DFS makes any contribution, whether BFS is in aggregate a bit faster than DFS. It's hard to tell, but we don't have that data. But here I've tried plotting it by number of components, and unfortunately the data is essentially meaningless. And one of the reasons I know it's meaningless is because these spikes are clear. What's clearly happening here is that there is no clear correlation, at least on this data, between the number of components and the running time. And that's sort of nice because what that's telling us is the running time of the algorithm doesn't seem to correlate to the output, that is the number of components. It correlates more to the number of vertices and edges. And the number of vertices and edges is sort of related to the number of components. That is, if you have too many edges, you're eventually going to have fewer components. But that this plot, to me, I reflect on this as meaning essentially that we shouldn't interpret there being a particular strong relationship between the number of components and the running time of the algorithm. All right, so there's our breather. That was a weird breather, but we definitely have our knowledge of the disjoint set structure down, so when we need to talk about it in the next lecture, where it's going to show up randomly in the middle, we will now know that it's definitely pretty fast. So we've proven absolutely that it's always going to be better than log n performance, although it turns out in practice it's way better than that.